So, welcome to module P2. So, this is basically done to address some of the frequently asked questions in the project, so that this helps you to finish the project faster. So, again I insist that this course, for it to be fruitful to you, you have to do the projects. I hope you are doing it well and you are in the midst of finishing your project too. So, we will give you certain inputs that will be extremely useful for you to finish the project quickly, and whatever I am going to talk today will make lot more sense if you had actually tried and you had been having some issues. And also please do write all your issues on the discussion forum so that you get quick responses. Do not wait for the modules to complete. You can keep progressing well. You can use the book, you can use the online source, and you can actually make some progress earlier, so that when you actually sit through the lecture it becomes much more fruitful for you. Now module P2 is some facts in project that you have done so far. So let us take this. R16 is a chip that you have designed, which will take 16 bits and 16 combinations of bits A, B, and it will give you a 16 bit output, which will be out I is equal to AI or BI, I going from 0 to 15. So that is R16. So it takes two vectors A and B of 16 bits in length, and it generates an output vector which is again 16 bits in length. Out I is AI or BI. Okay. Now in some other chip ABC we are using the same R16, wherein we say A equal to K, B equal to R, out equal to T. Let us assume that K, R and T are internal variables, they are not part of the input output. We have already seen in the module P1 that K, R and T automatically assumes to be a 16 bit vector, right. They are automatically assigned as a 16 bit vector. So you need not explicitly say that K is a 16 bit vector. Since it is actually assigned to A, which is a 16 bit vector, K becomes a 16 bit vector. Similarly R becomes an 16 bit vector, same as T, right, where K, R, T are internal variables not described as part of the in and out, right. So this we had seen in project P1. Now let us see some very interesting things. Now suppose I define a chip ABC where A and B are inputs of 16 bit vectors and out is another R is an output which is 16 bit vector. I instantiate several chips inside. So let us say XXX is some chip and T is an input variable to that. So I can take T equal to A7 to 9, right. So I can take part of the input and assign as input to that module. Similarly I can say R5 to 8 is equal to say some T1, right. So this is some input of, so let us take this as XSB, some XXB or something like that. So XXB has an input which we call it as R, some 16. Now I can assign T1 any variable as part of that input variable. So both of these are correct. So what we are saying here is that if I have an input variable and I am instantiating a chip inside, I can take part of that input variable and assign it to that T, right. Similarly if there is an input of another chip which is which has a vector, I can assign part of that vector to some variable T1 here. So T1 essentially is should be a 4 bit variable here, okay. So both of these are correct. So so these two will be supported. Now let us see what will not be supported. For example, I have chip in out, right, R16 A equal to T. Now so T actually now becomes a 16 bit vector, right. Now T is an internal variable, it is becoming a 16 bit vector. your simulator, your hardware simulator, which we call it your hardware simulator that you are working on, will not allow this. I can't take an internal variable and then use a part select on that, right. So, I am instantiating some other chip X where B is part of this internal variable. If it was a part of input output, yes, but if it is a part of internal variable, I can't split it like this. So, this your hardware simulator does not permit. Okay. So, you should be careful while doing this. Similarly, if I have an out variable out, okay, let us take this is out 16 for example, I can't make part of that output be equal to something, right, first and foremost. So, I can't do a part select on the output. And more than that, if suppose let us take this case which I am marking here, if B is not the output variable of some module XSX, B is an input variable of that module, then I can't assign out to that input variable. So, the output variable cannot become an input to some other chip which is instantiated within that, right. Please note that in this case XXX, the third case I am talking of here, XXX, B is an input variable to XXX, B is not an output variable of that. To that I can't assign the output variable of the chip. The output variable of the chip is out, that I can't assign to an input variable of some other chip. So, these three are very important. So, to summarize, the hardware simulator does not support a part select of an internal variable. In this case T is an internal variable, since it has been used with A equal to T on R16, T becomes a 16 bit vector. I can't use the part select of an internal variable assigned to something. I can't do a part select of an output variable, in this case out, I can't do that, and similarly I can't assign a part output variable of the chip to an input variable of some other chip that I am instantiating here, right. So, these three are important conditions that you should basically look into very carefully when you are designing your hardware. So, right, these are some limitations of the, or I do not know, we can't call it limitation, these are all some of the rules or constraints that are imposed by your hardware simulator. Nevertheless, if you follow these rules, your actual design becomes much more readable or much more verifiable, right. So, now let us go to the next part. So, you would have been designing the ALU. So, just to summarize, ALU had NX, sorry, NZ, NX, let me just do that, it has ZX, sorry, ZX, NX, ZY, NY, F, NO, 6 input control lines, right. So, this has been explained well in the previous module. So, let us take, so the ALU gets two 16 bit vectors, namely X and Y. Now, how do we work on this? So, let us put, this is a mux 16. So, we just put a mux 16, we also put another mux 16 here and basically give false, false means 0, right. So, false, and the control select is basically ZX and ZY, right. So, if you give ZX, the output will be 0, if this is, so this is 1 and this is 1 and this is 0, similarly this is 1 and 0, okay. So, if ZX is 1, output is 0, otherwise it is X, similarly ZY is 1, output is 0, otherwise it is X, right. Now, we proceed to the next stage. So, this output we take, we invert it, similarly this output and invert it. Note that each are all 16 bit lines, all of them are 16 bit, this is also 16 bit and this is also 16 bit. Now, we basically give again to a mux 16 and we give here nx and we give here ny mux 16 and we give here ny. So, this is again this is 0 1 and this will be 0 and 1. Now, look what is happening. So, if nx is 0, then whatever comes out of this mux 16 will come out here. If nx is 1, whatever came out of this mux 16 gets inverted and you get it here. So, that is what, right. So, this is the x you have defined, this is the y you have defined, that x will become not x if nx is 1, y will become not y when ny is 1, otherwise it passes on. So, this is the next thing. Then you basically have an adder, the 16-bit adder, and you will have the 16-bit AND, right, and you basically give these two inputs and also these two inputs. So, x and y you give it to both. So, you will get an answer here x plus y and you will get x and y here, right. Now, again give it to your mux 16 and here the input will be f and this is 1 and this is 0. If f is 1 it is x plus y, f is 0 it is x and y. I will again take this input and give it to another mux where you put NO, this is 0 and this is 1 and this is your final output. This is your final output. Okay. So, now you actually see how the control signals are playing a role and how the data flows. So, note that the control signals basically guide the data through that path. Okay. So, which data should go where, the control signals basically do this. So, all the control signals are controlled to the multiplexers here, right, and so the multiplexer actually route which data has to go, which will decide at every stage what is the data that needs to be proceeded. So, Zx Zy decides whether x should go or 0 should go, y should go or 0 should go. After that the nx ny decides should I invert that value of x or not, then it is getting added and then this mux will decide should I give the adder's output or the AND output, and then finally the last mux decides whether should I invert the output or not invert the output. So, this is how the ALU is constructed. Please note that this is essentially a very modular design. We have already done mux 16, we have already done add 16, we have done un 16, just we have to write a small code which will be some 5 to 10 lines to basically do this whole project and it will work. Now, once you go to alu.hdl and basically we can go to alu.hdl and basically you can go ahead and look at this file. So, this is going to be a very simple small file. So, this is the total thing that we need to do. Okay. So, this is a small file in that, so small set of code that we need to write. I am just leaving it as an exercise for you to do. Then what we need to do is after you finish this ALU, then of course there is a test file and there is a compare file. The test has two parts, ALU no status, this is one test where there are two flags that come out, namely your ZR and NG, two flags that come out, whether say that the answer is 0 or the answer is less than 0, answer is negative. So, what I have described so far, we have not coded the flags, right, the status flags. So, basically you can use this ALU no stat to test your ALU so far, where there is the status flag is not output. Then you can use the normal ALU TST file, which will include the status flag also. This will include the status flag. So, you can do the ALU in two stages. The first ALU is that do not include the status flag, then you can include the status flag circuitry, and then you can do this ALU.tst before you do ALU no stat.tst. So, there are two test files for testing the ALU, one with the status flag and one without the status flag. First do without the status flag to see that it works properly, then do with the status flag after you code that part. So, let me just go and show that part. So, how do you generate the status flag? One thing is you can take the output, and if you take the output and all of them, if you take the output and OR all of them, if the R is 0, that means ZR should be 1, right. Basically you can OR all the bits, right, R equal to 0, then ZR will become 1. So, this is one part of the story. So, this output we take and we OR all the bits of this output, and then you get ZR equal to 1. If that OR is 0, that means none of the bits are 1, the output is 0 0 0 0 0 0 16 times. So, it will become 0. So, you have to do an OR 16 way, right. You could have done an OR 8 way. So, we can use 2 OR 8 ways to do this OR 16 way. The second thing is negative NG. The NG flag, you have to take the most significant bit of this out, and if that most significant bit MSB of out, which is out 15, if this out 15 is 1, then NG is 1, else it is 0. Okay. So, this is how you basically find the NG flag, and this is how you basically find the ZR flag, right. Now, the challenge that you will be facing here is that you can't take this output and input to any other module, as just I have told you in the previous things. Like if this is an output, that output variable cannot be given assigned to any input variable of any chip that I am instantiating. So, you can't just go and say that you can take this output and give it to a module which basically goes and tests some part and come out. Okay. So, what we need to do is we may have to go and make it as a temp out, okay, and this temp out, so you may have to invert it 2 times to get out. Okay. Now, this temp out actually becomes an internal variable, and this internal variable I can take it out to check, and to assign temp out equal to out, right. So, there is no buffer that we have, that is which will take this temp out and give out an out. So, I have to invert, I have to put 2 not 16 here basically to get an out here. That is the only way by which I can assign out to temp out, right. There is nothing like a buffer which will just carry this value and assign it. Out and temp out are the same, but there is no way by which I could express it using our built-in chips or the chips that we have designed. So, we have to put 2 knots to get an output there, right. Then this temp out you can tap to basically start using to basically get your NG and your ZR, okay, right. So, this temp out can be used on an R8 way, 2 R8 ways, and we can do, but please also note that this temp out being an internal variable, I cannot split it. This temp out is a 16-bit variable, right. So, this is a 16-bit variable, this is a mux 16. So, this is a 16-bit variable, again I can't split it as 0 to 7 and 8 to 15, that is not possible here, because as I told in one of the rules, an internal variable we can't do a part select on a internal variable. So, this temp out has to be treated together, and we have only an R8 way, we do not have an R16 way. So, that also we need to keep in mind, right. And secondly, I can't take a part select of a internal variable. So, I can't even get this temp out of 15, which if it is 1 then ng is 1. So, I can't get temp out of 15. So, essentially I have to do something to, I have to generate 2 other modules or chips to basically handle this. So, there will be a small challenge here, I will leave it as an exercise for the reader to basically get your ng and ZR correctly tested. After you code that ng and ZR into your ALU.HTL chip, then you can use your ALU.TST. Currently without this ng and ZR module, you can use the script ALU no stat, and if with this we can actually use the script, this is ALU no stat, and once you code for the ZR and ng flag, then you can use your ALU.TST. Till then you use the ALU no stat.tst. So, these are some of the things which will help you to quickly finish your project ALU, right, and I hope this is going to be useful. If you have any other doubts, please do put in the discussion forum and we will respond to it. It is very important that you finish this ALU before you start looking into the third module. All the very best. I hope you are enjoying this course. Thank you.